Okay. So last time we were discussing chapter 4, prime numbers. Okay. We also discussed the greatest common divisor of two numbers, the GCD of A and B, as well as the least common multiple of two numbers, A and B. All right. And we talked about how to find the GCD and the LCM using the prime factorizations of A and B. And we also talked about how to find the GCD, the greatest common divisor of A and B, using the Euclidean algorithm. Okay, so anyone have any questions about that stuff or any questions from the homework? Okay. All right, so today we are going to continue what we started last time. At the very end of class last time, I gave you an introduction to mathematical induction in chapter 5.1. Chapter 5, section 5.1. We're going to continue with that today. Let's see, somebody has a question here. Not going over the exam. Not yet. So the exam grades have been posted. So everybody, you should be able to see your exam grade. If you don't see your grade, then let me know. Please send me an email. All right, and I'll let you know when we'll go over the exams. Okay. Will there be a curve? No, there won't be a curve. Okay. All right. Any other questions about anything? All right. All right, so let's continue in section 5.1, induction. Okay. All right, so just to go over what we were discussing last time, induction is a proof, a way of proving that certain theorems, certain mathematical statements are true. Okay, so anytime you have a mathematical statement in the following form, you have a statement that says some propositional function, P of n, is true whenever n is from some set of consecutive integers. So any statement that says P of n is true for a set of consecutive integers. Okay. So for example, if you have a statement that says P of n is true for all positive integers, meaning the integers from 1 and up, or P of n is true for all non-negative integers, so from 0 and up, or P of n is true for all integers greater than or equal to 10. Okay. Any statement like that, we can prove it's true using this method, using induction. So statements of this form can be proven using mathematical induction. Okay. Yeah, this is what we briefly introduced 5.1 at the end of class last time, so it's 5.1 continued. Yeah. Okay. So how does induction work? So induction, again, if you can complete the 2 steps of mathematical induction, you can prove that the given statement is true. Okay. So how does induction work? So we said last time that there are 2 steps. So induction has 2 steps. Okay. Step 1 is called the basis step, we said last time. Okay. So in the basis step, what do you have to do? In the basis step, you have to verify, or you have to show that the propositional function P of n is true in the first case, meaning for the first or the smallest possible value of n. Okay, so show that P of n is true for the smallest possible value of n. Okay. So by way of example, last time I said if your statement is P of n is true for all positive integers, then in your basis step, you have to show that P of n is true for the smallest positive integer, which is 1. Okay, that's your first case. Okay, so that's what you do in the first step. That's the first step of induction. Okay, you have to show that that's true. In the second step of mathematical induction, this step is called the inductive step. Okay. You have to prove that the conditional statement, if P of k, then P of k plus 1 is true. So show that if P of k, then P of k plus 1 is true. Right? Where k is an integer that has the same domain. Well, k is, I should say, an arbitrary integer that has the same domain as n. Let me say arbitrary. Okay. All right. So in your inductive step, you're basically doing a proof of a conditional statement. Okay. Usually we'll just do a direct proof. So you want to prove if P of k is true, then P of k plus 1 is true, where k is some arbitrary integer from the given domain. Okay. So if your statement originally said P of n is true for the set of positive integers, then k is some arbitrary, meaning some random positive integer. Okay. Okay. So if you can do these two things, if you can, in your basis step, show that P of n is true for the smallest possible value of n, and in the inductive step, you can show that whenever your statement is true for some arbitrary value, for some arbitrary integer k, it must be true for k plus 1. Okay. These two steps combined prove that the given statement is true. Okay, and we explained a little bit why last time. I'll explain again why now. It's sort of like you're setting up a domino effect. Okay. The second step tells me that P of n is true for some value k. If it's true for some value k, then it must be true for the next value, k plus 1. All right. Combine that with the first step. The first step tells me that P of 1 is true. Okay, that the first case is true. The second step, the inductive step, tells me that when P of 1 is true, the next case, P of 2, also has to be true. Okay? And once P of 2 is true, again, apply the inductive step again, P of 3 has to be true, right? If you make k 2 now, then k plus 1 will be 3. And once 3 is true, again, apply the inductive step again, 4 is true, and so on and so forth. This goes on forever and ever, okay, up to infinity. Okay. So that's the idea behind induction. So like I said, it's like a domino effect. So the second step is like lining up all the dominoes so that when one falls, it knocks over the next one. And the basis step is like knocking over the first domino. Okay, so that's sort of the idea here. Okay, so any questions on the idea behind induction before we see some examples? Yes. Yeah, that's correct. So you first prove that the first one is true, that the smallest number is true. That's correct. And then you move on to the second step. Okay. Right. Well, no. Well, you'll see. Let's do an example, and so you'll see how so to speak, how this works. Okay. Let's do an example together. All right. Okay. Okay. So last time I had given you a statement as an example of something that you can prove using induction. Let me write that statement down again. Okay. So we're going to show that if n is a positive integer, then the summation formula is the following summation formula is true. So then 1 plus 2 plus 3 plus dot 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 all the way up to n, right? That's the sum of the first n positive integers, equals n times n plus 1 divided by 2. Okay. So we want to prove that this statement is true using induction. All right. So the first thing that we're going to do is we're going to identify what is our propositional function. What is P of n? All right, let's do that first before we get to the 2 steps for mathematical induction. Okay. So what is P of n in this problem? Okay. So in this problem, P of n is just the summation formula. It's the statement that 1 plus 2 plus 3 all the way up to n is equal to n times n plus 1 over 2. So P of n is the statement 1 plus 2 plus dot 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 all the way up to n equals n times n plus 1 divided by 2. That's our P of n. Okay. What is what I've been referring to as the domain for this problem? In other words, what is n allowed to be? N is any positive integer. Okay, so this is saying for all positive integers n, this summation formula is true. So n is a positive integer. Okay, that's, so to speak, our domain. Okay. All right, so now once we understand what P of n is, and we know what our domain is, let's now move on to the induction part. So we're going to start with step 1, the basis step. Okay, so we're going to prove that this formula is true, that this formula works for all positive integers n using induction. Okay, so in our basis step, we have to prove that P of n is true for the smallest possible value of n. In this problem, what's the smallest value that n is allowed to be?
1.
Yeah, 1. Yeah. Mm-hmm. Right. N is any positive integer, so 1. So we have to show that P of 1 is true. Okay, so in other words, we want to show that when I plug in 1 for n into P of n, that this statement is true. So the statement is an equation. So if it's P of 1 is true, that means the 2 sides of the equation should be equal when I plug in 1 for n. Okay, so let's see, what is P of 1 going to be? So if I'm plugging in 1 for n, okay, the left-hand side of the equation is 1 plus 2 plus dot 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 all the way up to n. So if n is 1, what does the left-hand side of my equation look like? Okay, I'll put an equal sign here. What does the left-hand side look like? If n is 1, what's on the left-hand side? Yeah, just 1. Okay, right? It's the sum of all the positive integers up to n. So if n is 1, on the left-hand side, all I have is 1. Okay. What about on the right-hand side? I have 1 times 1 plus 1 over 2, right? I'm just plugging in 1 for n. Okay. So if this equation is, if the statement is true, then this equation should hold, right? The left-hand side should equal to the right-hand side. Let's see if that's true. This would be 1 equals 1 times 2 over 2, which is the 2's cancel. I'm left with 1. So 1 equals 1. Ah, it works. Okay, so check, it works. Okay. So that's it for the basis step. We verified that the statement works. It's true for n equals 1. Okay, P of n is true when n is 1. Any questions on that before I move on to the second step? Okay. Why is the left side 1? Okay, let me explain that again. All right. Let me scroll back here for a moment. This here, P of n, is a summation formula, right? The left-hand side is the sum of the first n positive integers. Okay, so meaning I'm going to add up, starting with 1, I'm adding up 1 plus 2 plus 3 plus 4 plus 5, and I stop whenever I get to n. That's what the left-hand side means. So if n is 1, and I'm going to start at 1, and then I'm at 1, so I don't have nowhere to go. So I stop at 1. Okay? So it's not 1 plus 2, it's just 1. Okay. And just maybe to make that a little bit clearer, let me just maybe rewrite this, right? 1 plus 2 plus 3 plus ... plus n, right, let me just, is the same thing as, I'll write it on this side. The sum from n equals 1, from I equals 1 to n of I, right? So if n is 1, it's just the sum from I equals 1 to 1 of I, which is just 1. How did you come up with P of n? Well, P of n is given to me in the question. It's always going to be, the statement will be given to you in the question, okay? So P of n is always the statement that you are trying to prove is true. It's the propositional function, all right? And then you'll also be given the domain in the question, right? So if I scroll back to the question, here it is. See, they gave me P of n. That's the statement I want to prove is true. And they also gave me the domain, right? N is a positive integer. So those two things should always be given to you in the question, okay? Okay. Sometimes it won't be very, the wording won't be so clear, but you will always be able to figure out what that statement is that you're trying to prove. Okay, but it should somehow be given to you in the question. Okay. All right. Any other questions before I continue? Okay, so far we have completed our basis step. So we're halfway done for induction, okay? To complete the proof, we have to complete the second step, the inductive step. So we have to show that if P of k, then P of k plus 1 is true. We have to prove that conditional statement is true for some positive integer k. Okay, so k is allowed to be whatever n is allowed to be. N is allowed to be any positive integer. So k is some arbitrary positive integer. Okay. Some randomly chosen positive integer. Okay. Okay, so this is what we want to prove. We want to prove if P of k, then P of k plus 1. Okay, so we're going to do a direct proof. We're going to assume P of k is true and use that to show P of k plus 1 is true. Okay, so I'm going to do a direct proof. Use direct proof. Okay, let me start by writing down what P of k and what P of k plus 1 actually are. Okay, what is P of k? To figure out what P of k is, I'm going to go back to what P of n is. Okay, P of k is just P of n. I just take out the n and replace it with k, right? It's a propositional function. It's a function. Just replace n with k. So P of k will be 1 plus 2 plus ... all the way up to k, whatever k is. And that will equal to k times k plus 1 over 2. So I'm just replacing n with k. What will P of k plus 1 be? Same thing. I'm going to take out n and replace it with k plus 1. So it's going to be 1 plus 2 plus ... plus, let me leave a space there for a second, plus k plus 1. Okay, you don't really need the parentheses. I'm just putting parentheses to make it a little clearer. And that should equal to k plus 1, right? So I'm replacing n with k plus 1 times k plus 1 plus 1 divided by 2. Okay, so for P of k plus 1, wherever I had an n, I replaced it with k plus 1. All right. Okay, so let me ask you, what number comes right before k plus 1?
K.
Yeah. Does everybody see that? Yeah. Hopefully that makes sense to everybody. This is a set of consecutive integers. So the number right before k plus 1 is k. Okay, this is a sum of consecutive integers here. All right, so that's a k there, and that's space that I left before. Okay, so let me just simplify this a little bit. This is 1 plus 2 plus ... I just wanted to make clear that that was a k there. I'm not going to write it again. Okay, it's hidden there in the 3 dots in my ellipses. Okay. And I'm going to simplify the right-hand side a little bit. It's just k plus 1 times k plus 2 divided by 2. Okay, so this is p of k plus 1, and above it is p of k. All right. Okay, so any questions on that so far? All right. So we're going to do a direct proof. How do we do a direct proof? We assume that the hypothesis is true. So we're going to assume p of k is true. Okay. Then we use that hypothesis, use the assumption that p of k is true. Okay. And this assumption is called the inductive hypothesis. The inductive hypothesis. To show that p of k plus 1 is also true. Okay, so we want to show that when p of k is true, p of k plus 1 has to also be true. Okay. All right, so we're calling this assumption that p of k is true, we're calling that the inductive hypothesis. Okay, right. Okay, so let me start this proof here, this direct proof, by assuming p of k is true. So I'm going to start by writing down p of k. Okay, so let's start with p of k. What was p of k? Let's write it down again. It was 1 plus 2 plus ... plus k, and that equals to k times k plus 1 divided by 2. That's p of k. Okay. All right, so I want to get from p of k to p of k plus 1 somehow. All right, I want to show p of k plus 1 is true. So I have to derive p of k plus 1 from this equation. Okay. So let me scroll up here for a moment. Looking at just the left-hand sides of p of k and p of k plus 1, okay, if I'm starting, and again, so looking at just the left-hand sides here, if I'm starting with p of k, what do I have to change? What do I have to add to it to get to p of k plus 1? Yeah, that's right. You have to add k plus 1, okay? Looking at just the left-hand sides of p of k and p of k plus 1, to go from p of k to p of k plus 1, I've got to add k plus 1. Okay, that's the only difference. Okay, so that's what I'm going to do here. I want to get to p of k plus 1. So I'm going to add to this equation k plus 1. But since I'm adding it to the left-hand side, to keep the equation equal, I have to add it to both sides. Okay, so I get 1 plus 2 plus ... plus k plus 1 equals k times k plus 1 divided by 2 plus k plus 1. Okay. Now, because p of k is true, anything that I do to it algebraically or arithmetically will also be true, right? So because p of k is true, if I add 2 to both sides, that equation will also be true. If I multiply both sides by 5, that equation will also be true, and so on and so forth, right? So any algebraic manipulation that I do will also be true, right? The equation will still be true. Okay. All right. So on the left-hand side, I've got 1 plus 2 plus ... I'm not going to write the k again, even though it's technically still there. It's just hidden now. Okay. It's included in my 3 dots. Now let's look at the right-hand side for a moment. I want to add here, but I've got a fraction. To add fractions, they have to have a common what? Yep, common denominator, exactly. So I'm going to have to multiply this k plus 1 by 2 over 2. So that we'll have a common denominator, and then I can add. So I've got k times k plus 1 plus 2 times k plus 1 divided by 2. All right, let's now add this together. So to add this together, I first have to distribute here. So I'm going to distribute the k and the 2. k times k is k squared, plus k times 1 is k, plus 2 times k is 2k, plus 2 times 1 is 2 over 2. Okay, adding the like terms. All right. This is going to be 1 plus 2 plus dot 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 plus k plus 1 equals k squared plus 3k plus 2 over 2. Okay. All right. Now k squared plus 3k plus 2, I can factor that. If I factor that, what will my factors be? What are my factors going to be if I factor that? Right. Well, I need, k plus 1 and k plus 2, right? Why? Because I need two numbers that multiply to give me 2, whose sum is 3, so 2 and 1. So my factors will be k plus 1, k plus 2. Okay, right, when I multiply those, I get back k squared plus 3k plus 2. Okay, let me stop here now. I'm going to scroll back for a moment, one moment here. Now remember, we assume that p of k is true. Okay, so I wrote down p of k. So any mathematical manipulation that I do will also be true, right? As long as I do it to both sides. So I started with p of k. I did some mathematical manipulation to it, and I ended up with this thing. What is this thing that I now have in front of me? What is that I now have in front of me? Does that look familiar? All right, let me circle it. Yeah, this thing here. What is this thing? Same as the conclusion. Yes. Well, what do you mean by conclusion? If I scroll back up for a moment, you'll notice that that is p of k plus 1. All right, this is p of k plus 1. All right. So I started with p of k, and I algebraically manipulated it until I got p of k plus 1, right? See, notice how it's exactly the same. There's p of k plus 1. I'm going to scroll down again. Here's p of k plus 1. So this is p of k plus 1. So I started with p of k, and I was able to derive from it p of k plus 1, the conclusion. So I started with the hypothesis, and I showed that if the hypothesis is true, if p of k is true, p of k plus 1 can be derived from it, which means p of k plus 1 has to also be true. Okay, so that means that the inductive step is now complete. So we have shown that if p of k, then p of k plus 1. So we derived the p of k plus 1 summation formula from the p of k formula. So we've shown that that is true. Concluding the inductive step. Okay, so our two steps are complete. The basis step is complete. We know that p of 1 is true, and we know that the inductive step is complete. So whenever p of k is true, p of k plus 1 is true. Okay, so that tells us that since we know p of 1 is true from the first step, this step tells us that p of 2 also has to be true. Okay, right? 1 plus 1 would be 2, right? If 1 is k. Once we know p of 2 is true, the inductive step tells us that 3 has to be true. Once it's true for 3, it has to be true for 4, and so on and so forth for all the positive integers. So therefore, the proof is done, and we've proven that the statement is true using induction. So therefore, we have shown that p of n is true, right? The original summation formula for all positive integers n using induction. And we are done with this proof. I'll put a little box. Okay. All right, so any questions on this problem or on induction in general? Because that's it. That's all you have to do. Once you complete the two steps, induction tells us that the statement is true. Okay. So we have a question here. How do we use the information given about the domain? Well, the information about the domain, we use that for the basis step. That tells us where to start, what our smallest integer is. Okay, so that tells us where to begin in the basis step. Any other questions? Oh yeah, we're going to do more examples of this, don't worry. Okay. All right, so let's move on to some other examples. So this was an example of using induction to prove a summation formula. All right, I'll give you some homework problems to practice these, okay? So this was, if I scroll back here. All right, so this was, let me just write it here. Okay. So this was an example of induction for a summation formula. Okay, so anytime you use induction to prove a summation formula, all right, in the inductive step, you start with whatever the equation is for P of k, and you manipulate it to derive the P of k plus 1 equation. Okay, so whatever we did here is what you're always going to do, basically, right? So you will look at the left-hand sides. What did we do? We looked at the left-hand sides. I saw what I had to add. I added that to both sides, and I continued from there. Okay, so all those problems, you'll have some practice problems to practice that in the homework, but they're all basically the same idea. Okay, it's following the same steps, just with different summation formulas. All right. Let's try a different type of problem that uses induction. Let's try a problem for divisibility. Okay, or with divisibility. Okay, so induction can also be used to prove divisibility results about integers. Okay, so let me give you an example of that next. All right, so let's use induction to prove that n cubed minus n is divisible by 3 whenever n is a positive integer. Okay. So that's the statement we want to prove. This is a divisibility problem. Okay, we want to show that n cubed minus n will be divisible by 3 whenever n is a positive integer. That's what we want to prove. All right. So before I get to the two steps of induction, again, I'm going to let's first clearly write down what P of n is, what the statement is that we're trying to prove. And we'll also write down what our domain is. Okay. So the statement we want to prove is the statement that n cubed minus n is divisible by 3. That's what we want to prove. N cubed minus n is divisible by 3. Okay. Another way of writing this is to say that 3 divides n cubed minus n, right? In other words, 3 divides n cubed minus n. Okay, that's just another way of saying it. Right, or 3 is a factor of n cubed minus n. What's our domain here? Our domain for n is the set of positive integers. So n is a positive integer. I'll just write it this way. N is an element of z plus. Okay. All right, so we have our statement P of n, our propositional function that we want to prove. We know what the domain is, what n is allowed to be. Let's now move on to our two steps. So we go to the basis step. Again, since n is a positive integer, again in this problem, the smallest value for n, the smallest possible value for n is 1. Okay, that won't be the case in every problem. The most common cases are where the smallest value for n is either 1 or 0, but you could have n being, the smallest value of n being anything, really. Okay, so show that p of 1 is true. Okay, so we're showing that p of n is true for the smallest possible value of n. The smallest positive integer is 1. Okay, so if n is 1, then p of 1 is the statement 1 cubed minus 1 is divisible by 3. Okay. All right, let's see. 1 cubed minus 1 is equal to 0. Is that divisible by 3? Yes. 0 is divisible by 3. Or in other words, 3 divides 0. Okay. How do I know? Because 0 divided by 3 is an integer, right? 0 divided by 3 is 0. So it's an integer. So it's divisible by 3. Okay, so it checks out. So far, it works in the first case. Okay. Any questions on that? Okay. We're going to now move on to the second step, the inductive step. Okay. In the inductive step, we need to show that if p of k, then p of k plus 1 is true for some positive integer k. All right, and again, why is k a positive integer? Because n is a positive integer, so k is allowed to be whatever n is allowed to be. Okay, so let's again start by writing down what p of k and p of k plus 1 is. Again, we're going to do a direct proof, okay? But I want to start by writing down what p of k is and what p of k plus 1 is, so it's clear to us. All right. P of k is going to be the statement that, so let me go back to p of n. P of n was the statement 3 divides n cubed minus n. So P of k is the statement 3 divides k cubed minus k. Okay. P of k plus 1 will therefore be the statement 3 divides k plus 1 cubed minus k plus 1, right? Wherever I have an n, I just replace it with k plus 1. Okay. So P of k plus 1 is the statement that k plus 1 cubed minus k plus 1 will be divisible by, or is divisible by 3. Okay. So we're going to do a direct proof. Okay. I'm going to assume P of k is true. So what does that mean? That means what we assume that k cubed minus k is divisible by 3. Okay. We need to show that P of k plus 1 is true. So use this to show that P of k plus 1 is true. That is, we want to show that k plus 1 cubed minus k plus 1 is divisible by 3 as well. Okay, so any questions before I continue? Okay, before I do the proof, the direct proof here. Okay, So for this divisibility problem, what I'm going to do is I'm going to actually maybe work backwards a little bit. I'm going to sort of, as opposed to starting with P of k and getting P of k plus 1, I'm going to go straight to P of k plus 1. And then when a P of k becomes needed, then I will use it. Okay. So let's start with P of k plus 1. Start with P of k plus 1. Okay. So that says that 3 divides k plus 1 cubed minus k plus 1. I want to show that this is true. Okay, we don't know it's true. We want to show that it's true when P of k is true. Okay, so let's look at k plus 1 cubed minus k plus 1. All right, let me expand this thing a little bit. What is k plus 1 cubed? K plus 1 cubed that's k plus 1 times k plus 1 times k plus 1 minus k plus 1, minus k plus 1, yeah. Okay, so k plus 1 cubed is that. So that equals this. All right. If I multiply this, what am I going to get? I'm going to get k cubed plus what? All right, I get k cubed plus 3k squared plus 3k plus 1 minus k plus 1. Right? That's, if you remember Pascal's triangle, it's 1, 3, 3, 1 are the coefficients. If anyone remembers that. Okay, if not, that's fine. Okay, so again, what am I doing? I want to show that this statement is true. So I want to show that 3 divides this. Okay. All right, now what I'm going to do next is I'm going to do some rearranging here. Okay. I have here, well, first of all, I've got 1 minus 1. 1 minus 1 is 0, so that's canceled. That's gone. Okay. Now what do I have? I've got k cubed plus 3k squared plus 3k minus k. Okay. So you might be tempted to do 3k minus k and get 2k, but I don't want to do that yet. Okay. Instead, what I'm going to do is, like I just said, I'm going to rearrange this here. All right, I'm going to rearrange this and rewrite it as k cubed minus k plus 3k squared plus 3k. All right. Now, why am I rearranging it like this? I'm rearranging it like this so that I get k cubed minus k, right? I just put the minus k more towards the beginning. Why do I want k cubed minus k? Because where have I seen k cubed minus k before? If I scroll back up for a moment, k cubed minus k, oh, that was in the P of k statement. Okay, and I want to use P of k to show that P of k plus 1 is true. So I rearranged it so that I see k cubed plus k cubed minus k, so that I can use P of k. All right. Now, we assume that P of k was true. That was our inductive hypothesis. Okay. So what does that mean? If P of k is true, that means we're assuming k cubed minus k is divisible by 3. Okay, that was our assumption. Okay. So k cubed minus k is divisible by 3 by our inductive hypothesis. Okay, we had assumed that that was divisible by 3. That's from P of k, right? P of k. All right. Let's now look at 3k squared plus 3k. Is 3k squared plus 3k divisible by 3? What do you guys say? Yes or no? Is just 3k squared plus 3k, is that divisible by 3? We have one yes, because 3 is a factor. Does everyone agree? Anyone disagree? Everyone's too busy writing. Okay, I'm taking notes. Okay. Well, you're right. Yes, you're correct. 3k squared plus 3k is divisible by 3. How do I know? Because I can write it as 3 times k squared plus k, right? I can factor out 3. That means 3 is a factor. If 3 is a factor, that means it's divisible by 3. So this is, so 3k squared plus 3k is divisible by 3 because it has a factor of 3. Okay, that's what divisible by 3 means. That means 3 is a factor. Okay. All right, so I have here two things that are divisible by 3, right? The first one is divisible by 3 because that's the P of k. That was my inductive hypothesis where we assumed P of k was true. And the second thing is divisible by 3 because it has a factor of 3. So if I have two things that are divisible by 3, then we know, what do we know about their sum? We know that their sum will also be divisible by 3, right? That's a theorem we did back at the beginning of 4.1, right? If A divides B and A divides C, then A divides their sum. A divides B plus C. That was all the way back at the beginning of 4.1, okay, last week. So if 3 divides the first part and 3 divides the second part, 3 divides their sum by that theorem. So therefore, 3 divides their sum. No, you don't have to state the theorem. All right. Okay. I'll write it here just to remind you. So, this is a theorem from 4.1. All right, and then the theorem was if A divides B and A divides C, then A divides B plus C. Okay. So that means that P of k plus 1 is true. When P of k is true. Okay. So as long as P of k is true, meaning as long as 3 divides k cubed minus k, then P of k plus 1 is true. Then 3 will divide this, right? 3 will divide this, okay? This here. I'm going to scroll back for just a moment, right? If 3 divides this, then following up with the equals, that means 3 divides this, k plus 1 cubed minus k plus 1. So that's divisible by 3. Okay, so the inductive step is complete, and the proof is done. Okay. Questions on this problem? If you have to go, yeah, you can go. All right. Have a good day. Any other questions? Okay. All right, so again, the two steps were complete, the basis step and the inductive step, combining them together. That's mathematical induction. So by induction, we have proven that the statement is true, that n cubed minus n will be divisible by 3 for any positive integer n. Okay. All right, there is now a third type of problem that I want to discuss that we can use induction to prove, okay, and that's inequalities, okay. So we can also use induction to prove inequalities. All right, so let's just try the following. Okay, use induction to prove that n is less than 2 to the power of n for all positive integers n. Okay. All right, so again, let's start by writing down what P of n is, the statement we want to prove. we want to prove the inequality. So P of n is the inequality, that n is less than 2 to the n. Okay, and the domain is the set of positive integers, and is an element in Z plus, and is a positive integer. So again, the smallest positive integer is 1. So in our basis step, we prove P of 1 is true. So show that P of 1 is true. Okay, so if I plug in 1 for n, I get 1 is less than 2 to the power of 1, which is the statement 1 is less than 2, which is true. Okay, so P of 1 is true. Oh, yeah, sure. Let me scroll back here. Is that good, or do you need me to go back up more? More? Okay, sure. Should I go up a little more? No, that's good. Okay. Okay. All right, so next is our inductive step. Oops, sorry. All right, so we have to show that if P of k, then P of k plus 1, this conditional statement is true for some positive integer k. Okay. So again, we want to do a direct proof. Okay, so direct proof. So assume P of k is true. And use P of k. And again, that's the inductive hypothesis, the assumption that P of k is true. Use P of k to show that P of k plus 1 is also true. So let's write down, again, we're going to write down what P of k is, and we'll write down what P of k plus 1 is, okay? For P of k, it's just the inequality from before. I just replace n with k. So P of k will be the statement k is less than 2 to the power of k. P of k plus 1 will be the statement k plus 1 is less than 2 to the power of k plus 1. Okay, so the k plus 1 there is the exponent on 2. Okay, so for this problem, again, I'm going to start with P of k, just like I do with the summation formulas. So start with P of k, okay? So I'm going to start with the statement that k is less than 2 to the power of k. So this is true by the inductive hypothesis, right? So this is true by the inductive hypothesis. Right? K is less than 2 to the k by the inductive hypothesis. It's an assumption. We're assuming it's true. Okay. All right. Now, if I look at the two inequalities, I want to go from P of k to P of k plus 1. So again, looking at the two inequalities here. Oh, somebody had a comment? 1 second. No, I think it's good. Okay. Looking at the two inequalities here, looking at the left-hand sides here, from k to k plus 1, I just got to add 1. Okay, so I'm going to add 1 to both sides. Right? It's an inequality, so as long as I do the same thing to both sides, it won't change. The inequality will still hold. So I'll have k plus 1 should be less than 2 to the k plus 1. Okay. All right. Now note that 1 is less than 2 to the k. Okay. How do I know that 1 is less than 2 to the power of k? Because what's the smallest value k is allowed to be? The smallest value k can be is 1. So the smallest thing that 2 to the k can be is 2 to the power of 1, which is 2. Okay, so 2 to the k will always be more than 1, right? Because k is greater than or equal to 1. Okay. So that means that this thing, 2 to the k power of k plus 1, is less than 2 to the k plus 2 to the k, right? Because 1 is less than 2 to the k. All right, so did you follow me on that? Any questions on that before I continue? Okay. Right, so again, if 1 is always less than 2 to the k, then 2 to the k plus 1 is always less than 2 to the k plus 2 to the k. All right. All right, so what is 2 to the k plus 2 to the k? If I combine those, that's equal to 2 times 2 to the power of k. All right. And what is 2 times 2 to the power of k? Well, same base, different powers, so I have to add the powers. That's 2 to the 1 times 2 to the k. That's 2 to the k plus 1. So what do I have here? I have that k plus 1 is less than or equal to, well, it's less than 2 to the k plus 1. Right? So k plus 1 is less than 2 to the k plus 1. Does that look familiar? It should. That is p of k plus 1. Okay. So we have just shown that, I'm going to scroll back for a moment. When p of k is true, when k is less than 2 to the k, it must be that k plus 1 will be less than 2 to the power of k plus 1. Okay, so we're done. The direct proof is finished. And we finished the inductive step. Okay, and this problem is over. Okay. All right, questions. Let's see. It switches to an equal sign. Oh, no. It didn't switch to an equal sign. What I had here, let me rewrite it here. I had k plus 1 was less than 2 to the k plus 1. Oh, sorry. Plus 1. I had this, right? So just the right-hand side is equal. That right-hand side is less than 2 to the k plus 2 to the k. Okay. And that thing is equal to 2 times 2 to the k, which is equal to 2 to the k plus 1. All right. Can you explain the 2 to the k again, please? Do you still have that question? Or no? Okay, good. Any other questions? Okay, so I just rewrote what I did above as one line instead of multiple lines. Okay. So remember, it's an inequality. So as long as I show that it's more than, right, I'm good. All right. Okay. Let's try another one with inequalities here. Let's say I ask you, use induction to show that 2 to the n is less than n factorial for every integer n with n greater than or equal to 4. Okay, so again, this is an inequality problem. Yes, somebody had a question? Okay, I guess that was an accident. This is again an inequality problem, but here our domain has changed. Right now, n is every integer greater than or equal to 4. So p of n here is the statement 2 to the n is less than n factorial. That's what we want to prove is true. Okay. And our domain is n is greater than or equal to 4, right? And where n is an integer. Okay. So just as a reminder before we continue, what does n factorial mean? N factorial is n times n minus 1 times n minus 2 all the way down to 1. Okay, so in other words, let's say n was 5. 5 factorial would be 5 times 4 times 3 times 2 times 1. Okay, and then just by definition, 0 factorial is 1. Okay, basis step. All right, the smallest possible value for n in this problem is 4. So we have to show that P of 4 is true. Okay. What is P of 4? So replacing n with 4, that would be the statement 2 to the power of 4 is less than 4 factorial. Let's see if that's true. 2 to the power of 4 is 16. 4 factorial is going to be 4 times 3 times 2 times 1, which is 24. 16 is in fact less than 24, so that statement is true. It holds. Okay, so it works when n is 4. Let's now move on to our second step, our inductive step. Okay, we want to show that if P of k, then P of k plus 1 is true. Where k is an integer greater than or equal to 4. Okay, so k is some arbitrary integer greater than or equal to 4. So again, let me write down what P of k and P of k plus 1 are. P of k would be the statement 2 to the k is less than k factorial. P of k plus 1 is the statement 2 to the k plus 1 is less than k plus 1 factorial. Okay. So we're doing a direct proof. So we're going to assume P of k is true. Assume P of k is true. That's the inductive hypothesis. And use it to show that P of k plus 1 is also true. Okay, so again, I'm going to start with P of k. Let's write down what P of k is. Okay. Okay, so P of k is the statement 2k is less than k factorial. So let's start with P of k. All right, and that's by the inductive hypothesis. Okay, so what I'm going to do is I'm going to go step by step, but I'm just going to sort of write down what I'm doing on the right-hand side. Okay. All right, so we're starting with the assumption, our inductive hypothesis, the assumption that 2k is less than k factorial. Okay. All right, so looking back at P of k and P of k plus 1. Looking at the left-hand sides, okay, how do I go from 2k, algebraically or arithmetically, how do I go from 2 to the power of k to 2 to the power of k plus 1? What do I have to do mathematically to 2 to the power of k to get 2 to the k plus 1? Yeah, you have to multiply it by 2, okay? So what I'm going to do here is I'm going to multiply both sides by 2. Multiply both sides by 2. Okay, so what I'm doing is I'm manipulating algebraically the left-hand side of P of k to get it to be the same as P of k plus 1, and then I want to end up on the right-hand side with k plus 1 factorial. Okay, so we're going to manipulate until we get what we want. All right, 2 times 2 to the k is less than 2 times k factorial, right? If I multiply by 2 on the left-hand side, to keep the inequality true, I have to multiply by 2 on the right-hand side. All right, so 2 times 2 to the k, that's just 2 to the k plus 1, as we said. That's less than 2 times k factorial. Okay, now, do you agree with me that 2 is less than k plus 1? Is 2 always less than k plus 1? No. Somebody says no, so why not? All right. Let's think for a moment. What is the smallest number that k can be? Right. So if the smallest number that k can be is 4, then the smallest that k plus 1 could be is 5, right? So k plus 1 will always be 5 or more. So k plus 1 is certainly more than 2. Okay, is that clear? Got it? Yeah, okay, great. Okay. All right. 2. So 2 is always less than k plus 1 because k is greater than or equal to 4. All right. All right. Now, why am I... So what does that mean? That means that 2 to the k plus 1, which is less than 2 times k factorial. Okay. 2 times k factorial will be less than k plus 1 times k factorial. Okay, why? Because 2 is less than k plus 1. So 2 times k factorial is less than k plus 1 times k factorial. Okay. Does anyone have any questions on that before I continue?
Can you explain the last part again?
Yeah. 2 times k factorial, this thing here, is less than k plus 1 times k factorial. How do I know? Because 2 is less than k plus 1, which is what we just said over here. Okay, so 2 times k factorial therefore has to be less than k plus 1 times k factorial.
No, I got it. Thanks.
Okay, great. All right, now why did I choose k plus 1 to put over here? Because I'm keeping in mind, right, let me scroll back for a moment. You got to keep in mind, I want to get from k factorial, I want to get k plus 1 factorial. Okay. What do I have here now? Now I've got k plus 1 times k factorial. Let me get rid of that circle there. Okay. Now I've got k plus 1 times k factorial. K plus 1 times k factorial is the same thing as k plus 1 factorial. Okay, does everyone see that? Would anyone like me to explain why that is? Yeah, okay, sure. All right, let's write this out for a moment. We have here, for a moment, let's just write it on the side, k plus 1 times k factorial. What is k factorial? If I write it out, k factorial is k times k minus 1 times k minus 2, dot, 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 all the way down to 1. Oh. Okay, so I have here k plus 1 times k minus 1, dot, 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 all the way down to 1. By definition, that's k plus 1 factorial, right? That's k plus 1 times k minus 1, etc. So k plus 1 times k factorial is k plus 1 factorial. Okay. Okay, great. Okay. So what have we just shown? We've just shown that 2k plus 1 is less than k plus 1 factorial, right? So 2, this was... So 2, let me write it here. 2 to the power of k plus 1 is less than k plus 1 factorial. This is p of k plus 1. Okay. So we just showed that when p of k is true, p of k plus 1 is true. So the proof is done. The inductive step is done. And by the logic of induction, our statement is true for all positive integers n greater than or equal to 4. Any questions on that? Okay. If there's no questions, we are done for today. Let's do the attendance. Okay. Oh, I see we still have some questions. Okay, so I'll answer those questions while you guys do the attendance. And I will post some homework for you guys to practice this stuff over the weekend. And on Blackboard, so keep an eye out for that. Okay. Again, if you didn't see your grade posted on Blackboard, just send me an email to let me know. Okay. But your grades should all be up. Let me see. We had a question here. What happened to 2 times k factorial? And somebody also asked when the final is. Okay. Oh, also about the quiz. Yes, there will be a quiz on Monday on chapter 4. Okay, somebody asked about that. Okay, nothing on chapter 5, just chapter 4. Okay. We have class on Tuesday next week? Wednesday? I prefer to do it earlier. So I prefer to do it on Monday. Okay. Okay. Oh, that's tough. All right. Let me ask. No, no problem. Let me answer this question first about the 2 times k factorial. Okay. So again, what happened to 2 times k factorial? Well, it's an inequality. So all I said was that 2 times k factorial is less than k plus 1 times k factorial. Okay. It doesn't have to be equal, it just has to be less than because it's an inequality. All right, so 2 times k factorial is less than k plus 1 times k factorial. And again, because of the reason that I explained before, that 2 is less than k plus 1. Okay, check again. If you still don't see it, then yeah, send me an email. Okay, and I'll take a look. Okay, for your grade. All right. For the final, give me a second. I'll look up what the date of the final is. That sounds right. Let me just double check for the final date. Give me 1 second. Yeah. Our final exam will be Wednesday, December the 16th, from 4 to 6 p.m. Okay, this is December the 16th from 4 to 6 p.m. You should be able to look it up on CUNY First and on Blackboard. Oh, wow. All right, that's tough. Okay. Again, the final will not be cumulative. It's only going to include the new stuff we've done since the second exam. So it's only going to be chapters 4, 5, and 6. Okay. Okay. All right. I gotta go. Take care, everybody. Have a great day. All right. I hope everybody put their name for the attendance. I will see you all next week. Keep an eye out for the homework and a quiz. We have a quiz on chapter 4 on Monday. Take care, everybody.